Hello everyone, welcome back to the second lecture of Chapter 2, Kinetic Particle Theory. So in Lecture 1, we looked at the arrangement and the movement of particles in the three states of matter, and we also looked at evidence that proved the kinetic particle theory, including Brownian motion, diffusion, as well as other pieces of evidence that allowed us to conclude that matter was made up of small discrete particles, and these small discrete particles are in constant random motion. Now let's move on to apply our understanding of kinetic particle theory to explain properties of shape and volume, which you might have learned in primary school as well as lower secondary science. So in this section, we will be looking at how we can use the movement and arrangement of particles to explain some of the properties of solids, liquids, and gases. Now first, let's start with the properties of shape. I think all of us are familiar with terms like fixed shape, no fixed shape. So we know from primary school science that solids have a fixed shape, whereas liquids and gases do not have a fixed shape. So what does it mean for something to have no fixed shape? So no fixed shape means that it can flow freely. The particles in liquids and gases are able to flow freely, and when they do so, they will take whatever shape the container they are in is. So let's say if I were to pour a liquid into a container that is rectangular, that's cuboid, it will take the shape of the cuboid. On the other hand, if I were to pour the liquid into a round container, then it will take the round shape of the container. So the idea here is the shape depends on whether the particles are able to move freely or not move freely. And this is where we apply our understanding of the movement of particles. So let's begin. Solids have a fixed shape, and this is because particles of a solid are held together in fixed positions by very strong forces of attraction between them. So if you recall, this was what we did in lecture 1. We know that particles of a solid, they are actually vibrating about fixed positions. And the reason why they are in fixed positions is because there are very strong forces of attraction between them. So the particles are only able to vibrate about fixed positions and therefore cannot move freely. If the particles cannot move freely, a solid cannot flow and therefore has a fixed shape. On the other hand, if you look at B and C, a liquid and a gas doesn't have a fixed shape. And this is because in a liquid, the particles can slide over one another easily and therefore move freely to take the shape of whatever container they are in. And in a gas, the forces of attraction between the particles in the gas are weak, and hence particles are able to move freely in all directions at high speeds. So there is freedom of movement here in all directions at high speeds, and therefore, again, particles in a gas, they are able to take the shape of the container they are in. So basically, shape depends on the movement of particles, whether the particles can move freely or not move freely. Now we move on to properties of volume. So we have learnt in primary school as well, solids and liquids have a fixed volume, while gases do not have a fixed or definite volume. Now, what does it mean to have no fixed volume? If the volume is not fixed, this means that it can be compressed when pressure is applied. So gases can be compressed easily. Now, why is it that gases can be compressed easily? The idea is the particles are spaced very far apart. Now, please correct this typo error. No fixed volume implies that the particles are spaced very, very far apart. So like in a gas, gases do not have a fixed volume because the particles in a gas are spaced very far apart in a random or irregular arrangement. So solids and liquids have a fixed volume, and this is because the forces of attraction between the particles are strong and the particles are closely packed together. When the particles are closely packed together, they have very little spacing between the particles, and hence a solid and liquid cannot be compressed when pressure is applied, and hence the volume remains fixed. It doesn't change under pressure. On the other hand, gases do not have a fixed volume, and can be easily compressed. This is because the particles in a gas are spaced very far apart from one another, and there's a large amount of space between the particles, which can be decreased when pressure is applied onto the gas. So for instance, we can have a plunger that plunges down to compress the gas, like in this case. When we compress a gas, what we are doing is that we are actually decreasing the spacing between the particles. So under high pressure, gases can be compressed, the particles can come closer together. And this is possible because there was initially a lot of spacing between the particles of gas, which are spread very far apart from each other. So we have basically covered the properties of shape and volume, which can be explained using the movement and arrangement of particles in the three states of matter. Now, we are going to delve deeper into what happens when a solid is heated or when a gas is cooled down. And this can be represented on a graph of temperature against time or heat added. Okay? So this can be either heat added or time on the x-axis, whereas on the y-axis, it's temperature. Now, this is a heating curve because you can tell the temperature goes up with time. Okay, so let's begin. So the idea is, if you look at this curve, it's made up of 5 distinct sections, A, B, C, D, and E. We will look at each section one by one. So the idea is I am actually heating up a solid. What happens to this solid as it's being heated up? How does the temperature of this solid change? So let's start in section A. So in region A of the graph, you can see that the temperature goes up. So what is happening to the particles as temperature goes up? First, we will need to know temperature is proportional to the average kinetic energy of the particles. Meaning, the higher the temperature, the higher the average kinetic energy that the particles will have. So you can see in region A, the temperature goes up. This means that the particles will have higher kinetic energy, and therefore, higher kinetic energy means the particles will move faster. As the particles move faster, the spacing between the particles will increase slightly. Okay, and that's region A, as the solid is being heated up. Now, when looking at a heating curve, what's interesting are the regions where temperature becomes horizontal. No change in temperature. Like in region B, there is no change in the temperature because it's flat at region B. Now, when there's no change in temperature, temperature has remained constant. This is where there is a change of state. Meaning, in region B, the solid is changing state. So what is happening? Region B is where the solid turns into a liquid. The solid is melting. And therefore, during melting, there is heat energy that is taken in, absorbed from the surroundings. And the idea is the heat energy taken in during melting is completely, fully used for 2 purposes. Number 1, to overcome the forces of attraction between the particles. There is a need to overcome or weaken the forces of attraction between the particles, because we know that in a liquid, the particles are spaced slightly further apart compared to a solid. The particles are less closely packed in a liquid than a solid. That only happens because the forces of attraction were overcome or weakened. Now take note, we use the word overcome. We will never say break. Break is a wrong word to be used because break implies that the forces of attraction are totally gone. But that is not true at all. There will still be forces of attraction between particles in liquids and gases, just that they get weaker and weaker. Hence, break is a wrong word to be used with forces of attraction. Never ever use the word break. We are referring to overcoming the forces of attraction between the particles. And of course, because the forces of attraction are overcome, the spacing between the particles will therefore increase. Okay? And crucially, because we have used the heat energy completely to overcome the forces of attraction and to increase the spacing, there is no increase in kinetic energy and speed of the particles. If we go back to the central concept, temperature is proportional to average kinetic energy. If there is no increase to kinetic energy, temperature remains constant. And therefore, during melting at region B, the temperature remains constant. And this temperature is called the melting point. So we can deduce the melting point of a substance from the heating curve. We go to the y-axis where temperature is. We look for where the graph becomes flat, where melting happens. We trace it back to the y-axis. Over here is minus 60 degrees Celsius, and that is the melting point of the substance. So we say that the melting point of this substance is minus 60 degrees Celsius. And during melting, the solid continues to be in this process of changing into a liquid, and temperature remains constant. This means that during melting itself, we have both solid and liquid coexisting in equilibrium. So during melting, you don't just have solid, you don't just have liquid, you will have both solid and liquid states present, coexisting together during melting. Okay? And of course, melting will continue and temperature will remain constant until melting is complete. Now, when melting is complete, the graph continues to increase. So that's region C. You can see the temperature continues to increase in region C. And this is because melting has been completed. So in region C is entirely liquid. And the temperature continues to increase as the particles in the liquid gain kinetic energy. They move faster, and hence the temperature increases. But there will come a point where the liquid reaches its boiling point. And you notice that is where region D is. Region D. Again, there is no change in temperature because it's completely flat, the graph. This indicates there is a change in state. So now what is this change in state? Originally, it was a liquid. So the liquid must be turning into a gas. Therefore, this is the boiling point. So we say that the boiling point of this substance is 60 degrees Celsius. So again, you notice at region D, the temperature remains constant because it's undergoing boiling. During boiling, it's the same as melting because it absorbs heat energy from the surroundings. The heat energy absorbed is fully used to overcome forces of attraction and to increase the spacing between particles. There is no increase in kinetic energy or speed of the particles, and hence the temperature remains constant. And similarly, because it's still boiling, during the process of boiling, you will have both liquid and gaseous state present. Okay? So you must be able to explain why temperature remains constant during melting and boiling. Now, these are important explanations in terms of particles that you must learn. Now, besides that, from this graph, we can also tell that boiling requires more energy than melting. You can tell from this graph that boiling requires more energy than melting because from the length of the line segments of B and D, region D, which is boiling, occurs over a longer period of heating. You can tell that the boiling took a longer time and heating in order to be completed. And this tells you that changing from liquid to gas, boiling, will take in more energy than changing from a solid to a liquid. Okay, so not only can you get the melting and boiling points, from the length of the line segments of B and D, you can actually tell and conclude that boiling requires more energy. Okay, now Finally, the final piece of information you can get from the heating curve is that this substance is actually pure. How can you tell that from the heating curve that this substance is pure? So we learned in chapter 1, a good way to tell purity is to look at whether it has a fixed melting point and boiling point. So you can tell from this graph that the melting point, it melts at minus 60 degrees Celsius. The boiling point, it boils at 60 degrees Celsius. That means it melts and boils at a fixed temperature. During melting, the temperature remained constant at minus 60. During boiling, the temperature remained constant at 60. So this is a pure substance. So what will an impure substance actually look like? For an impure substance, the heating curve will look like this. You can see that the temperature is not constant during the melting and boiling. Alright, so for an impure substance, you can tell it very easily when you plot the heating graph, because you can tell that during the melting and boiling, it occurs over a range of temperatures. Okay? Range of temperatures. And that's it for the heating curve. So from the heating curve, you can learn many things and conclude many things, including why temperature remains constant, why boiling takes more energy to happen than melting, and finally, telling whether something is pure or not. Okay, so now, the reverse of the heating curve is actually the cooling curve. When we cool something down from a gas to a liquid and then to a solid, now you can see, well, this is actually just the reflection, the mirror image of the heating curve. Where you start with the gas, then you have condensation, then freezing. Now, importantly, condensation is from gas to liquid, and this occurs at the boiling point. Boiling point is where condensation happens. It is also where boiling happens. Then, we have freezing. Freezing occurs at the melting point. Melting point is where melting happens. It's also where freezing happens. So, for instance, water freezes at 0 degrees Celsius. Ice melts at also 0 degrees Celsius. So we need to explain why is it that during condensation and during freezing, the temperature remains constant. So again, the explanation is very similar, but remember to reverse the words. Just now, heat energy was absorbed. Now heat energy is released, given out. So heat energy given out during condensation is fully used to make the forces of attraction between particles stronger, to decrease the spacing between particles. There is no decrease in kinetic energy and speed, and therefore temperature remains constant. So again, during condensation, you will have both liquid and gas present. So remember, during change of state, you will have both states present. During freezing, similarly, heat is given out. It's fully used to make the forces of attraction between particles stronger, decreasing spacing between the particles. There is no decrease in kinetic energy or speed, and the temperature remains constant as a result. And again, during freezing, change of state, you will have both the liquid and the solid states present, coexisting together in equilibrium. Okay, so the cooling curve really is related to the heating curve. The explanations are actually very similar because they are based on the same concept, that during a change of state, there is no decrease or increase in kinetic energy of the particles. Okay, so you have to learn the explanations well. Why is it that temperature remains constant during the change of state? And now you should be ready to complete checkpoint 2. So please complete checkpoint 2 questions before our next lesson in class. Now let me move quickly on to the very last page of this set of notes. How can we deduce the state of matter if I'm given the data on the melting and boiling points of the substance? So now I have 4 substances here, A, B, C, and D, with different melting points and boiling points. So how can I work out their state of matter at room temperature? Room temperature is defined as 25 degrees Celsius. So now we're going to focus only on substance A. You are told that substance A has a melting point of minus 134 degrees Celsius and a boiling point of 1 degree Celsius. What I would first do is I would mark out the boiling point and melting points. Melting point, minus 134, boiling point, 1. Now, after I've marked out the melting point, boiling point, I basically have 3 segments to this graph. Solid on the left, liquid in the middle, gas on the right. So this neatly divides my number line into 3 segments: solid, liquid, gas. The last step is to find out where 25 is on this number line. So where will 25 degrees Celsius be on this number line? Obviously, 25 degrees Celsius is larger than minus 134. 25 is also larger than 1. If it's larger, it must be on the right-hand side of 1. So 25 is larger than 1, therefore, it will appear to the right of 1. And look at where 25 is now. It's in the gaseous section of the line. And therefore, we can say that A is a gas at room temperature. Okay? Now, try to use a number line to help you solve such problems involving melting and boiling points. You might feel that this is quite easy for you, especially if you are good with numbers. But when you have negative numbers, you have to be careful to ensure that you do not get the numbers the wrong way round. So I strongly advise all of us start off by using a number line to complete the states of matter for B, C, and D. So please also complete these 3 questions in addition to checkpoint 1 and checkpoint 2 before our next lesson in class. And that brings us to the end of the second lecture of Chapter 2, Kinetic Particle Theory. Now, please review the lecture videos, both the first lecture video and the second lecture video today, to ensure that you have fully understood this chapter. When we come back to class, we will just be solving the problems. Alright? So all the best, and do approach me if you require further clarifications on the content covered here. Thank you.